Hi guys, and welcome back to the Ace Academy. In this video, we will be looking at transverse waves. Now, in order to grasp this section correctly, we are going to ask ourselves a few simple questions, such as, what is a transverse wave? How is a transverse wave created? What are the properties of a transverse wave? And how can we use these properties mathematically in order to solve questions that involve the transfer of energy? So without further ado, let's get started. Now, a transverse wave is created in a similar manner to how a transverse pulse is created. So to understand this concept, we are going to use the same model that we used in order to understand pulses. And that is simply a string with beats. We are going to record the magnitude of the displacement throughout this medium as energy progresses, as well as how the energy would progress as time passes. So looking at the first block in this diagram that we have sketched out, we can see that we have our medium at rest or at equilibrium. We are now going to introduce some sort of disturbance. And by introducing this disturbance, I'm basically going to pick up the first bead in this medium to a height of 3. This will in turn create a pulse, as you can see in the second diagram. So let's illustrate that graphically. I'm going to take this first bead right here and I'm going to raise it up to a value of 3. And if I let go and watch how this disturbance affects the medium, we can see that a transverse pulse is created with an amplitude of 3. Essentially, the energy is going to transfer from the first bead throughout this medium. Now, where transverse waves differ from a transverse pulse is a transverse pulse, we just disturb the medium, it's an isolated disturbance, and we watch how the pulse progresses through the medium itself. Whereas for a transverse wave, we are now going to continue to disturb this medium in order to obtain a continuous transfer of energy. So looking at the second block in this diagram, we can see that we have the pulse with an amplitude of 3. As soon as this first bead in this medium comes back to its rest position at 0, instead of watching the pulse propagate, we are now going to move this bead to a value of -3. So we are now going to move that first bead downwards. And what this does to the medium is it creates a second pulse in the negative region. So that's the opposite direction. So looking at the third block in this diagram, we can see that we now have a single pulse in the positive region and a single pulse in the negative region. This combination of pulses, one in the negative, one in the positive, is what we call a single wave. Now, if I were to continue this pattern of disturbances in the medium, if I raise the first beat back up to an amplitude of 3, and then after the first beat came back to rest, I disturbed it to an amplitude of -3, I would obtain a continuous waveform that looks something like the fourth block in this diagram. And as you can see, as it progresses onto the sixth block, the pulses would create this pattern of a wave. Keep in mind, a single wave is made up of 2 pulses, one in the positive, one in the negative. Now that we have a certain understanding of how a wave is created, we are going to look at some of the properties of a wave. Now, a wave can be measured in terms of its length using a quantity that is known as wavelength. This quantity is denoted by the symbol lambda, and that is that symbol that I just highlighted in blue for you guys. Now, wavelength is essentially the distance between 2 consecutive points in phase on a waveform. When I speak about 2 points being in phase, it will have the exact same disturbance level, energy level, as well as the exact same position relative to the significant points on the waveform itself. Let's look at this diagram on your screen. The apex of the first crest is in phase with the apex of the second crest. The apex of the first crest, however, is not in phase with the apex of the first trough, and that is simply because it does not have the same displacement, nor does it have the same relative position. Similarly, if I were to look at this point that I'm highlighting in turquoise, it is in phase with the second point that I'm highlighting in turquoise, and not in phase with the third point that I'm now highlighting in turquoise. And that is simply because even though this point right here has the same energy level or the same displacement, it does not have the same relative position, because this point is to the left of the apex of the crest, whereas this point right here is to the right of the apex of the crest. Hence, it cannot be in phase. Whereas if we look at this point right here, it is in fact also to the left of the apex, and it has the exact same energy level. Let's go ahead and test out this theory together. We are going to identify 2 points in phase on the waveform. Let's work with the apex of the crests. Those 2 points are in phase. If I wanted to calculate the wavelength, all I would have to do is take the distance of the second point, which is 7.5, and subtract the distance of the first point, which is 1.5, and I would obtain an answer of 5. And that is in fact the wavelength. Let's try this with 2 other points that are in phase on this waveform. Let's identify our points in phase. Let's go with that one and that one. If I were to calculate the wavelength using these 2 points, that would be 8.5 minus 2.5, which is in fact equal to 5. And that is the wavelength. You can see that the wavelength would be the same if we are working with the same wave, as long as we are working with points that are in phase to one another. So calculating wavelength is quite simple. We can determine that graphically when looking at a sketched waveform. Now let's look at the second property when it comes to waves, and that is the period of a wave. Now the period of a wave is denoted by the symbol capital T, and it is the time taken for one wave to pass a point. As you guys can see from the definition of the word period, it is dependent on time. So let's go back to our diagrams and see how the wave changes with respect to time. We can see initially we had a medium that was at rest. After a certain amount of time, once we introduced the disturbance, we can see that the first crest was formed. Then after a certain amount of time had passed, we can see that the first trough has been created. As we can continue, we can see that a new crest has been created as well, and I'm going to indicate that with the circle that I just drew in turquoise. Then at T4, this is half of a time interval. We can see that half of a pulse was created, and at T5, we can see that the complete new crest has been created. So all this wave is doing is transmitting energy from the first beat in the medium to the last beat in the medium, and then getting rid of that energy. The energy is being transferred out of the system. Now, in order to work with period, you are going to need some sort of time value on your waveform. So we will go ahead and do that together in the example that is to follow. The second wave property that relies on time is something that is known as frequency, and this can be denoted by the symbol 1 over t, which is the inverse of period, or it can be denoted by the symbol f. Now, frequency is measured in hertz, and it is essentially the number of waves that pass a point in 1 second. So period is the time taken for one wave to pass a point, and frequency is the number of waves that pass a point in 1 second. They're the inverse of each other. After analyzing the properties of these waves, we can see that a transverse wave will have some sort of distance measurement, which is the wavelength, and it would have some sort of time measurement, which is either the period or the frequency. Now, when we combine distance and time, we are able to work out the speed at which this waveform will travel. And this quantity is known as wave speed. And wave speed can simply be understood if we look at the formula for speed in general. Speed is in fact distance over time. If we think about driving in a car, we know that the speed of a car is measured in kilometers per hour. Whereas for us in physical science, because we are physicists in training, we would use SI units, which keeps our calculations uniform. So the SI unit for speed in our case would be meters per second. Let's break down the formula for calculating wave speed. We know that speed is distance over time, so let's apply that to the concept of waves. So the speed of the wave should be the distance of a single wave divided by the time it takes for a single wave to pass a point. Now, we can obtain an equation using the symbols for these properties. We know that the distance of a wave is in fact wavelength, and that is denoted by lambda. And the time taken for a single wave to pass a point is in fact the period, which is denoted by a capital T. So we obtain the equation for wave speed, which is the speed of the wave is actually the wavelength divided by the period. Now, using our mathematical algebraic skills, we can separate this fraction into v is equal to lambda times 1 over t, because lambda is wave speed, and lambda divided by t is the same as me saying lambda times 1 divided by t. That's an algebraic property. But as physicists, we now know that 1 over t, which is the inverse of period, is in fact frequency. So we can simply replace this 1 over t by the symbol f, which gives us the wave speed equation, which states that the wave speed is in fact the wavelength multiplied by the frequency of this wave. Now that we have covered the fundamental bits of theory that are required for us to understand this section, we can apply it in an example. On your screens right now, you can see that there is a simple question for us to attempt together. We have a sketched out waveform with a whole lot of properties assigned to it. Let's go ahead and get started. The first part of question 1 asks us to calculate the wavelength. Now, wavelength is a measure of distance, so we are going to look for some property that has an association to length. And we can see that the only property that gives us length in this diagram is the 0.2 meters that I've highlighted. Now, 0.2 meters is the distance from the first crest to the first trough. But hey, those 2 points are not in phase, which tells us that that is not the wavelength. So how would we work this out? We know that the distance from a crest to a trough is 0.2 meters. So what point is in phase with this first crest? That would be point A, which I'm highlighting now. And we can see that the distance from the first point of the first crest to the apex of the first trough is in fact the same distance from the apex of the first trough to the apex of the second crest. That tells us that in order to calculate wavelength, we simply have to multiply the length value that was given to us by 2. So that'll be 0.2 times 2, which is equal to 0.4 meters. The second part of this question asks us to state the amplitude. Now we know that amplitude is the highest possible disturbance or energy level in a waveform. So let's go ahead and look for the highest possible energy level in this waveform. We can see that the highest possible energy level in this waveform is in fact 3. So the amplitude is 3. Looking at question 2, it asks us what is the period of this waveform. So we are going to go back to our theory and think about what period is, what is the definition of period. And the definition of period is that it is the amount of time required for a single wave to pass a point. Let's look for some sort of time value on this sketch. We can see that along the x-axis, we have the time intervals of how the energy would look like as it passes through this medium. Let's look for a single waveform. A single waveform is simply 2 points that are a wavelength away from each other and are in phase. So looking at this diagram, we can see that the first point is the apex of the first crest. So we're going to look for the apex of the second crest. And we can see that this shape right here is in fact a single wave, because we have a single pulse in the negative direction. And if I combine these two halves, I'm going to I'm going to obtain a single pulse in the positive direction. We have a pulse in the negative and a pulse in the positive that creates a single waveform. So we are going to see how long it takes for energy from here to reach there. And that can simply be done by following the line of the apex of the second crest down to the x-axis, which has our time intervals, and we can see that that is 0.4 seconds. It takes 0.4 seconds for the energy from the first bead to reach the bead at point A. Question 3 asks us to calculate the frequency of the wave. We know that frequency is the number of waves that passes a point in 1 second, and this can be calculated as the inverse of period. We know that frequency is actually equal to 1 over t. Therefore, frequency is equal to 1 over 0.4, and that should be equal to 2.5 hertz. So we know that 2.5 waves pass a point in 1 second. The fourth question asks us to calculate the wave speed. In order to calculate wave speed, we are going to use the wave speed formula, and that is simply v is equal to lambda times f, where lambda is wavelength and f is frequency. Substituting in the values for wavelength and frequency, wavelength is 0.4, frequency is 2.5. Therefore, the speed of this wave is in fact 1 meter per second. Let's go ahead and look at the special question for this section. The special question in this example asks us how many waves will pass point A in 2 minutes. In order to answer this question, we of course have to work in SI units. So we are going to convert 2 minutes into seconds. That'll be 2 times 60 seconds because it's 60 seconds in 1 minute. And that is equal to 120 seconds. We know that frequency is the number of waves that pass through a point in 1 second. So we can simply multiply the number of seconds by the frequency to obtain the number of waves. And that is 120 times 2.5, which is equal to 300. So in 2 minutes or 120 seconds, you will have 300 waves passing point A. It's that simple, guys. All the best, and I will see you in the next one.